Hello everyone, good morning. I'm Barun Acharya and today I will be talking about protecting modern workloads with eBPF superpowers. I'll start with who am I? I work as a software engineer at AccuKnox, working on cloud security solutions. I've been associated with Google Summer of Code, LFX mentorship, both as a mentee and a mentor. I hang around at open source developers community. We are a small community at our university spreading love for open source, and I'm an undergraduate student. So I mentioned modern workloads in my talk title, but what I essentially mean is containers, perhaps containers paired with some orchestrator like Kubernetes. So how many of you are using containers at some scale today? Great. So with the advantages that containers provide, the adoption rate for it has increased quite drastically. But with the rise in adoption, so has risen the cyber attacks on the same. With modern vulnerabilities like Log4j, PwnKit, there's an ever more demanding need to enforce security in our containers. So I mentioned Log4j and PwnKit. So they essentially are 0 days. We usually have some sort of static analyzers for our containers which help us analyze what known vulnerabilities our containers are affected by. But vulnerabilities like 0 days, evasive malware, or privilege escalation attempts in our containers, they happen at runtime and they cannot be detected by static analyzers. So how do we deal with vulnerabilities that manifest at runtime? We deal with them at runtime. So the term container runtime security. So container runtime security involves the following aspects: detecting malicious activity, alerting the activity with some context, and preventing it. But you may ask, like, how do we exactly detect it? What's the context here? How do we prevent it? So let's go through an analogy. Let's imagine containers as a private apartment. A private apartment with John and Jane each have their own room. They have a kitchen for functioning and they have a maintenance staff to help around if something is broken. John and Jane value their privacy. Jane doesn't like if John pokes into her room. Neither does John if Jane does the same. But they both do like to hang around in the kitchen. They generally don't want the maintenance staff to roam around in the apartment. But in case something breaks, like the kitchen pipe is broken or the gas is not working, something on the lines of that, they need the maintenance staff around. Now, let's take this analogy back to containers. We have two applications here, Apache WordPress, MySQL. They each have their configurations and directories. They need shared library files to function. And then there are maintenance binaries like cat or ps which help us out when some things are broken. But what if the Apache WordPress app tries to access the MySQL directory, or the MySQL app tries to access the WordPress directory? We know that something is wrong here because they shouldn't be accessing each other's directory or files. And something suspicious is happening here. So now coming back to what I mentioned earlier, like container runtime security. Now we know what we need to monitor. We need to alert that what we detect, and with some context. With containers, we have thousands of them running at scale. And like we just cannot say that like cat tried to access the WordPress config. We need to tell you that it is running as part of Kubernetes cluster something, it is running in this container, what are the image, and stuff like that. So that's the context we are talking about. And like after we alert it, we need to take action on it, eventually prevent it. So let's first focus on monitoring and alerting the activity. So this is a workflow that I came up with. Like when a malicious activity happens, it triggers a lot of events in our kernel space. And a detection engine will go through those kernel events and detect which is the malicious activity and alert to us. But just the kernel events do not have all the context, as I mentioned earlier. So we need to integrate our detection engine with container runtime APIs like Docker, Containerd, and the container orchestrator APIs. And that's how we get the whole alert with context. But the important thing here is that we need to access the kernel events and filter them out. So what existing tools do we have to trace these events and detect these? We have audit D, ftrace, strace, and eBPF. The issue with the first three is that they are not programmable, and it is difficult to extend upon them. And to add some context, we need the tool to be extendable. So, eBPF. eBPF allows us to safely extend our Linux kernel in a programmable and performant way. There are hundreds of hooks available where we can safely hook onto and extract the information that we need. Let's go through a demo of what I am talking about. So we have this sample eBPF program which tries to detect events which are tries to detect any execution events. So we have two Docker containers here, IndiaFOSS demo 1 and IndiaFOSS demo 2, and we try to hook our eBPF program here. So our eBPF program is live now. If I try to access something here, I get an alert. Alert with container ID, container name, container PID, process name, and process PID. We can get a lot more information. It depends on how we program it and how we integrate it with other APIs. Similarly, if I try to access something in a different container, it will let me know that I try to access which and all the other details. How do we do this? We integrate our eBPF program with the Docker APIs, and that's how we get all the context for the malicious activity. What I'm doing here is not malicious, but you get the context. So we talked about monitoring the malicious activity and alerting the activity with some context. Now let's talk about taking action on it. What we can do is, once we get the alert or telemetry, the user or the system administrator can issue a sick kill or something in the lines of that to terminate that malicious activity. But by the time it reaches the sysadmin and by the time he takes it action, the malicious activity would already have done its job and extracted all the information that they intended to do. This is asynchronous enforcement. But what if we as soon as we detect it, we issue a denial for that activity in the kernel space itself? That would be great, because as soon as the malicious activity tries to spawn, we kill it there and there itself. And that's what inline enforcement is all about, which is important to container runtime security. So what tools and primitives do we have to have this Linux inline enforcement? We have LD preload, seccomp, Linux security modules. Let's go through each of them and see the pros and cons for them. We have LD preload, which acts as a user space control and overrides the dynamic libraries that each and every application try to access. But the issue is that applications which are built with Go and stuff, they do not use shared libraries at all. They have their own statically linked binaries. And so they do not go through LD preload at all. And thus, the attacker can leverage it here. Then we have seccomp. Seccomp sandboxes are applications. It is also supported by Docker. But the issue is that it's pretty strict. We have limited filtering options, and dynamic enforcement is not possible. Finally, we have Linux security modules. Linux security modules like AppArmor, SC Linux, and BPF LSM. These are mature ecosystem with 20+ years of development happening on them. They do not suffer from a known race condition called as time of check and time of use. But the issue is that they are not integrated with modern context. They are not integrated with containers and orchestrators. And each of their policy language has a steep learning curve. But then came BPF LSM. BPF LSM combines this eBPF programmability and flexibility with maturity of LSM hooks. So our final workflow would something be like, a malicious activity happens in our containers. We have eBPF programs to detect the malicious activity and alert to our security engine. At the same time, we have these LSM hooks to enforce our policies and not let the malicious activity trigger. And that's how our complete container runtime security enforcement works. But we have a tool already for that. We at KubeArmor are trying to solve this problem only. We integrate with LSMs, we integrate with eBPF, we integrate with all the cloud native orchestrators and containers, and provide you with this particular functionality for container runtime security enforcement. Let's go through a demo of how it works. Meanwhile, I set up the demo. If any of you used any of the security primitives I mentioned, like LSMs or LD preload, so like you might be like relating to the fact that how they have a steep learning curve and stuff. So now, so I have a Kubernetes cluster running here. I will, one second. Is it visible now? So we have the WordPress and MySQL I talked about in our earlier analogy, and we have KubeArmor running as a pod as well to help us enforce these policies. So I'm inside the WordPress app, and now I can access the config file I mentioned earlier with cat, and it has some secrets which shouldn't be accessible to normal maintenance binaries. So that's why we want to restrict this behavior and try to enforce the policies. So we have this sample policy to block the enforcement, like access of the config file from the binaries bin cat. And similarly, we can have like mentioned that it should be only be accessible to the Apache WordPress binary. So let's try enforcing this policy. Now if I try to access the config file, I get a permission denied. And I have all the context that I needed, like what's the enforcer here, what was the file, who tried to access it, and stuff like that. We have a lot of information here which can be useful to like analyze why the malicious activity happened and take actions on it for future vulnerabilities accordingly. A well-known way to attack a Kubernetes cluster is trying to access the service account token. But the issue is that our application sometimes needs those tokens. Like a container has a lot of binaries in it. But some applications need those access account tokens and some applications do not. So we try to enforce that only those applications that need it can access it. And thus we apply a policy for the same. So you have a policy to block the access to service account tokens. So if I try to access the service account token now with cat, it won't be possible because I have restricted it. But what if we try to use curl to access the same over the network? We see that we have been denied access and we are forbidden to use the same. And that's how enforcement is working for us. So that's how eBPF is helping us protect our workloads, both for observability and both for enforcement. And thank you. Any questions?
Thanks, Varun, for the talk. First question is around the toolchain. What kind of toolchain are you using to deliver package eBPF program? Is it libbpf or BCC? Because we are also trying to figure it out. But
we were using BCC for till now, but like we migrated to libbpf like 2 weeks back.
For their CORE.
Yes. Though we for core is only supported once, since you are familiar with it, core is only supported on later kernel versions which are BTF enabled. Okay. So we are like, if the kernel version is like enough and the BTF information is available, we use the core, but else we have some init containers to compile at runtime for us using Clang and LLVM.
Got it. That makes sense. And secondly, have you done the performance testing like on the hooks and probes? If let's say high traffic on let's say applying a hook on let's say network layer on the kernel, how does the performance goes up and down for eBPF program?
So the performance aspect is like, it's on the scale of nanoseconds usually. Like from what we have tested, like it's around 5,000 or 6,000 nanoseconds of overhead with with the eBPF programs. Cloudflare and Kinrock folks have done this analysis at a large scale, and they realized that especially for the network traffic, like IP tables had a bandwidth of 2 or 4 Mbps, while with eBPF they had a bandwidth for above 40 Mbps. So that's so the performance aspect, at least with respect to the kernel space, is not an overhead as such.
Got it. And last question, like that complete talk basically is like eBPF runs on the kernel and containers don't have, like they have shared kernels, right? So all of the things that you mentioned, they are not specifically limited to containers, right? All of these programs that you mentioned, they will work outside the containers.
Yep, they totally work. Like I can use it as a, we ship it as a system, we ship KubeArmor as a systemd package as well, and you can use that to enforce on your host as well, like directly on the application is directly running on the host. Just that containers are running at scale, so it's much more important to have context and low overhead on these aspects that I mentioned containers.
Thank
you. Hey, yeah, the few questions actually. So in the demo you showed here the KubeArmor working locally on your machine, but can you ran KubeArmor on the host system directly, right?
Right.
So can you also just run KubeArmor inside the container itself?
No, so KubeArmor is a privileged system here, and it needs to be run as part of the host. So like if you have distributed hosts and multiple hosts working together, KubeArmor will work as a daemon set on individual hosts. Though if with the help of the custom resources, we can manage it through the control plane itself. But the actual agent, the KubeArmor agent, runs on individual hosts.
Okay, so Tandy also mentioned that you can also have it to work with these cloud providers. So something
right.
like
so
the
in
GKE,
here,
I assume.
I'm running the KubeArmor as a pod in like a local Kubernetes cluster itself. Like I'm not running it directly on. So we do support EKS, GCP, and OpenShift as well. So
Okay.
yep.
So the KubeArmor container, so they will have to be the privileged container in that case.
Yes, like we have deployments, we have helper tools for help you deploy things, and we have the whole documentation which it explains like what are the permissions we require to deploy things, and
Okay.
yeah,
Yeah.
I don't have the network access here. You can log on to github.com. It's kubearmor.io. You can log on there and like explore the things there.
Yeah. All right.
Hey, very interesting talk. Thank you. I was just like in the last demo, you showed that you will manually list. So for given a configuration file, which binaries are supposed to or allowed to access it. Is there a way to like inspect a running application and then figure out like what do I need to whitelist? Because I mean, I would assume in a big application, it might be a little.
Yes. So like we have. So I just showed you the alerts which we detect as a malicious activity, but if we want, we can log filter equal to all. Now any access I do creates a telemetry event for us, like if it is allowed or not. And now since this is like, so I'm using this. So this is KArmor tool is our helper tool, which integrates with KubeArmor services and extracts the information. But you can build on top of it to extract the information KubeArmor on any of the applications you want. We have a like we call this tool a discovery engine, which analyzes these telemetry events and generates a policy for you to help out like enforce things. And the like as I understand that like since I demoed that only block things, it may be sometimes it is too restrictive to directly block things. We just want to see that if it is being how do you say that, like I just want to audit it, like I don't want to enforce things. So we like our policy, we can just block SA. I use this YAML file, right? So if I change the action here to audit, now the enforcement aspect will be removed, but we will still get like alerts, like for why, like so we deem it as malicious, but we just want to check if it is actually being accessed or not. So we can use these audit policies to help us with that. Okay, so okay, one second. I mentioned eBPF in two aspects here, probes and LSMs. So we can use eBPF for like just observability and eBPF for these LSM aspects. So probes do suffer, like the general syscall looks do suffer from like you can try to avoid it if you exploit a particular race condition, and you can like escape that observability aspect. But these LSM hooks, we can use it for observability as well as enforcement. But and these are like placed strategically in the kernel such that like any of these race conditions cannot be exploited, and we still have our observability and enforcement working as it is. Yep. Like they are like they LSM hooks are like clubbed for a few syscalls. So they have LSM hooks are placed such that when the all the syscall parameters are consolidated, then only LSM hooks like they go through the LSM hook and further processing happens. Okay. Thank you.